All right, hello. So today I wanted to give a very simple explanation of frequency, and I wanted to do this because I remember going into engineering and hearing the term frequency or kilohertz, megahertz, and I quite honestly got scared. It sounded complicated to me, so today I just wanted to simplify it. So if you're a musician, maybe you've heard the term or maybe you've seen the figure 44.1 kilohertz. That's usually a sampling frequency that they use in audio production. So I want to, by the end of that, hopefully you have a better understanding of what that means. And yeah, without further ado, let's just get into it. So I wanted to start off by asking this question: what is sound? And I know it's simple, but um, to get to what frequency actually is, we need to first define what sound is. So what we actually hear is actually caused by uh, so the sound is actually characterized by waves from a vibration or pressure change in a medium. So when I say medium, that could be air, that could be water, that could be a uh, guitar string, that could be the inside of this mason jar right here. This is a speaker on the top. So this medium actually acts as a part of that. So that's what sound is. So with that in mind, I wanted to show this picture here. This is an athlete that is um, he's throwing this rope back and forth, and it creates a little wave through this rope here. And if you can think of that image, let's say he's in the air and he's continuously doing it. Um, that's what we're going to talk about in a second, um, which we'll get to. But if the vibrations are actually fast enough, this would make a sound. So this athlete, he's actually not able to do it quickly enough. But if you were in the air, like I was saying, if this wasn't hitting the ground and you were just in free space doing that, if he was able to vibrate, go fast enough, that would create a sound. So how do we characterize it? Frequency. So what is frequency? The most simple way I could describe it is if you go back to this picture, if this athlete is continuously doing it, um, thinking of it like he's periodically doing it, right? He's doing it over and over again, like he's not stopping. Um, with that in mind, I would call it a cyclic vibration. So think of the guy just continuously doing that, moving that rope. But the frequency that we're going to be worried about is from 20 to 20 kilohertz. Now, what hertz is cycles per second. So you can think of that as um, one one whip of the rope would be one cycle. So here's what that would look like on a graph. So here's the guy standing right here, and here's the rope. So this would be one period from going from here to here. Okay. So like what I said about hertz, cycles per second, if this is time, let's say that this is 1 second right here. So if you count this out, going from here to here, if this is 1 second, you would have 1, 2, 3. Okay. So we have 3 cycles per second. So that would be 3 hertz. That's what this sine wave would be if that is 1 second right there. Okay. So the reason, so what I have here is I have a graph of 3 different uh, signals here. Okay. I have 2 sine waves of 2 different frequencies. So something to think about right here is looking at the blue sine wave and the black sine wave, think about which of these sine waves has a higher frequency. Okay, like with what I just said here, if this is 3 hertz, if that's 1 second, oops, and let's pick a point here. Let's say this is 1 second right here. Which of these two would be higher? Okay. So the answer would be this black one, because you have more cycles in a given time than the blue one does. Okay, so this would be a higher frequency. Now, what's cool about these sine waves is every single sound that we hear, think about what I said earlier about sound being by changes in a medium, vibrations and stuff. Every single noise that we hear is made up of sine waves. So this sine wave right here is actually the purest sound that we could ever hear, is just a simple sine wave looking like this. However, what we end up hearing is something like this red signal right here. Now, obviously, this is only 2 frequencies. Usually, every sound that we hear, whether it be my voice or music, or let's say you drop something on the floor and it makes a big bang, that's made up of a bunch of different frequencies added together. And I will show that with a visual explanation using this Desmos website. It's really useful, especially for XY coordinate plane stuff. So what I have here is I have 2 sine waves, and then I'm going to add them together. So let me first make our first one a higher frequency than the second one. Okay. So that should be, yeah, that should be fine for now. So think of this as hertz. Okay, so we have a 2 hertz sine wave and 1.5. I would do a larger frequency, but I'm not sure in Desmos how to make the graph to make the scale of the graph like lower. So just pretend like this 2 and 1.5 is on the scale of like 400 hertz to 600 hertz or something like that. This is just to visually show what's happening here. So we have a 2 hertz sine wave, and then we have 1.5 hertz sine wave. Okay, if we add them together, you get something like this. Okay, so what happens is when you have different frequencies, you don't get a very nice, clean looking signal. You're going to get something like this. And this is what we end up hearing. But what I was saying earlier, which is pretty important, is that I'm just adding these 2 together, right? These are 2 simple frequencies, but we end up hearing stuff like this. I don't know if you, like I've said this before, this looks like the Arctic Monkeys AM album, if you're familiar with that. But that's, this is what we would hear. A bunch of different stuff, a bunch of different frequencies added together. So yeah, that's just a little visualization of different frequencies being shown on a plot. Okay, so let me go back to slide format here. So a better way to understand frequency, by looking at it on a graph and trying to see what's going on there. What we do is a very useful tool that we use mathematically is called a Fourier transform. And what that is it's taking basically this frequency, this sine wave here, and putting it in what's called the frequency domain. So this is across time, like I said earlier. Remember counting the periods. That's based on time. But if we were to put this in frequency domain, because this is a pure signal, we would only see one frequency on the graph. Okay, same thing goes for here. Now I did this in MATLAB, and this doesn't look like a pure signal, but this represents a sine wave right here. So just pretend like this is a very pure. It's just something with the sampling or something in MATLAB like didn't make this look right. But as you can see, as we increase the frequency, we increase the number of periods per second, we have a higher frequency on the frequency domain. Okay, so this is very, very useful, especially for recording music. Okay, because if you want to see what the best way I could describe this is you're seeing what you're hearing. So you're seeing the different frequencies on a graph. So it's very useful for recording music because you can see what's going on. So to give you a visual of the frequency domain, what I did was I found this site, and let me make sure you guys can hear this computer sound. Okay, I did that. So what this is this is across different frequencies. So from 20 hertz to 20 kilohertz, which is what we can hear. This was an audio. This was an audio recording of a police siren. So what's going on here? If you could hear that in the video, hopefully you can. You can see that it's going back and forth. And remember the siren, it goes up and down. Wow, 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 wow. So this is the main thing that you're hearing, right? But notice that, and this is across frequencies, so the frequency is going higher and lower. So as frequency increases, the pitch increases. So we hear like a higher, we hear a higher note, if you can think of it that way. So it's going up and down. But notice that across the entire graph here, and we call this the frequency spectrum. The frequency spectrum just means the entire graph that you're looking at. All the frequencies that you can see on the graph is the frequency spectrum. Notice that with this recording, you can still see that it picks up noise along here. It's picking up other frequencies. Okay, if it wasn't, it would just be black across here, but it's not. It's picking up other noise. So that goes to show you that doing a Fourier transform on time domain signals is very useful because it shows what you're actually looking at. Okay, yeah, so hopefully you made a connection between the noise you're hearing and what is shown. And this is just another visual of the frequency spectrum. So like I said, from 20 to 20 kilohertz right there, these are a bunch of different instruments. And if you were to record one of these instruments, you would see the specific frequencies that it's highlighting. So let's say you play piano, you would hear it what would show up when you record it is from 20 to, what does it say, 50 kilohertz, 60 to 250. You would see a little bit of mid-range. You would see like 2 to 4 kilohertz, and maybe a little bit of overtones. Okay, so yeah, this is the frequency spectrum. So I already talked about I didn't mention what a spectrum analyzer. I mentioned what a Fourier transform is. So a Fourier transform is taking, like I said, that it's transforming the sine wave into one specific frequency. So it makes it easier to see what frequencies are in that signal. because the signal that you're looking at is going to be all over the place, right? It's not going to be a pure sine wave. It's going to be garbled, and it's going to look like nonsense. So it's taking the nonsense and putting it to different frequencies, and it scales with amplitude. So to see how loud those frequencies are in that signal. So that's what a spectrum analyzer does. It's doing that Fourier transform, and it shows it on a graph. An oscilloscope just takes in this whatever signal is in a circuit. So it's actually it actually shows on a graph in real time the signal that you're hearing, or the signal that is running through a circuit, and that's in time domain. So it would look like, again, like a bunch of nonsense. A signal generator creates a perfect sine wave. So these are very helpful for building anything audio related, especially guitar pedals. Because if you want to see how the guitar pedals operating, you don't want to play to test, to test the circuit. You don't want to play a guitar through it, because a guitar picks up a bunch of different frequencies. You just want to see what the guitar pedal is doing to one specific signal, or one specific sine wave with a frequency associated with it, to see how it operates on that signal, whether it clips it, whether it amplifies it, whether it delays it. So that's what this is for. MATLAB simulates signals. So if you don't have an oscilloscope at home and you want to see what is happening with a specific sine wave, if you perform an operation on it, operation, I mean some sort of equation or signal manipulation, MATLAB is very helpful, because as you can see, I actually generated these in MATLAB. So very useful for graphing stuff. And I actually have these two apps here. If you're still confused on, like, in terms of frequency, like when it goes higher, how is that associated to like what we hear, I highly recommend downloading this frequency generator. It has a couple options. It has some capabilities in here that are pretty cool. So first off, it goes from all the way from 1 hertz to 22 hertz, or 22,000 hertz. So if you just slide your, here, let me turn on lasers. If you slide from here to here, okay, you're going to hear a bunch of different pure tone, pure sine wave frequencies. Now you can also, by clicking, I forgot where it was in here, but there's an option in here. Oh yeah, right here. If you click on this, you can also do a square wave function. You can do a sawtooth, and you can do a triangle function, and that changes what's going on there. And I'll talk about it in another presentation. Is it's actually adding a bunch of different sine waves together to create a square instead of a pure sine, or also a triangle and a sawtooth. So really cool app for putting the visual and audio together. Now I talked about a Fourier transform. What's going on here is it's showing a graph, and it's also listening in real time. So if you were to, this is me talking into it right here, and you can see it picks up, since I have a really deep voice, it's picking up more deeper stuff. But if you want to test out, if you want to record your cat, if you want to put your, like, if you want to have your cat meow or squeal or whatever cats do, I don't have a cat. You can see where your cat falls in the frequency spectrum. So, very useful app. So Now that we've talked about frequency, I want to talk about a really important uh, aspect of that called resonance. So when you hear the term resonance, or like like you usually think of the term "this resonates with me," right? And when you hear that term, it's associated with someone telling a story, or maybe it's in a song, like lyrically, like especially in the rap genre, right? You hear like you hear a verse or something, and you're like, oh, this part hit me. People say like this hit me. Well, if you apply that same logic to the frequency spectrum, and you also apply it to a specific medium that the sound is in. So remember, I talked about medium, and I also gave this example right here of a glass jar. So that's why I have this picture of this little girl here, and she's blowing into glass bottles with different heights of, or with different volumes of water in it. So okay, so like I said, um, think of it like think of the frequency spectrum as like a paragraph or someone telling a story. You don't really care about this part of it or the end of it, right? You care about this one little thing that had meaning to your life, right? So think of your life as the medium. So this glass is the medium, and um, she's blowing into it, right? So she's blowing in the entire story, but only one little bit of it speaks out. Okay. So this is why when you blow into a bottle with different levels of water in it, one specific note speaks out from the rest. Okay. Because there are different resonant frequencies in here. There's different resonance associated to each medium. Okay. So think about when I talk through my throat, right? My throat is the medium. And because I have an Adam's apple, okay, my voice is going to sound different than that of a woman's. Okay, so that's something that you can think of it by simply changing the medium of something. You can also change the resonant frequency um, of that medium, and the resonant frequency is going to be the one that speaks out the most. It's going to be the loudest. I still have a bunch of different frequencies when I talk. Okay, so there's some higher frequencies in there, but the lower ones speak out more. Okay, so the best way to visually see what's going on here is, like I said, here's the frequency spectrum, this x-axis right here, and let's say for a specific medium, the it looks like for this one, the higher frequencies aren't really speaking out that much, right? And the lower ones aren't speaking out, but right here, right at this frequency here, it hits you, right? It resonates with you. It's like, oh, wow, look, that hit me, right? Like, listen to that. That's crazy. That's how you can think of resonance. Okay, so I wanted to show a visual of that in this YouTube video that I found. So what this guy did, this is called a Rubens tube. He has this long metal pipe, and what he does is he has a speaker attached to one end of it, and he's playing, and he and he has and he's playing a pure sine wave through it. Okay, so a pure frequency is going through it, and what he's doing is he's doing like he's going up in frequency. So he's doing a frequency sweep. What he's trying to do is figure out in this medium which frequencies speak out. Okay, and what he does is he has a little bit of gas that he puts in this medium, and he lights it on fire. Okay, so there's a bunch of different flames here you can see. And you'll see that as he increases the frequency, some frequencies are actually going to go higher. Okay, so it's hard to hear in the video, but
So hopefully you can see.
so that's what's going on there. Another analogy that I could think of this is think about playing a saxophone, right? And at the end of this video, he also plays a song through it. So it's not just he does a pure sine wave at first, but he also plays a song at the end. So there's a bunch of different frequencies going in here. But like I said, the resonant frequencies, the ones that speak out the highest in the medium, are going to be shown through these flames. It's pretty cool. But the example that I would give for resonant frequencies, another one is think about a saxophone. You're blowing through it, okay, and it's not going to be a pure sine wave, like I said. It's going to be a mixture of a bunch of different frequencies going through that tube, right? But based on which notes you play, that's going to change the resonant frequencies, and that's going to play different notes through the out through the end of the saxophone. Okay, that's what's going on there. You're just with saxophones and any wind instruments, you're essentially doing this. You're changing what this girl's doing. There's different amounts of water in here, and that changes which frequencies speak out from the others. Okay, you're blowing the same, you're putting the same sound through all of these, but different frequencies are going to speak out louder. And that's the same thing with saxophone, flute. What are some other ones? Trumpet. Um, all the wind instrument people are going to kill me for not knowing more examples, but like that's that's what's going on with resonance, and um, that's why you hear specific things louder than other things. Now, and resonance has uh, resonant frequency is not just applicable to the audio spectrum, 20 to 20k kilohertz or 20k hertz. Resonance is very important in RF applications. Um, as you can see here, I actually designed one of the things that we did in our RF class is design a what's called a resonator. So if you can apply this same logic to a circuit, what this thing is doing is it's only looking for a 915 megahertz signal, right? So if you were to put any other frequency through here, it wouldn't pass. But if it's 915, it would. Okay, so um, this idea of resonance and resonant frequency is very big in high frequency applications. So yeah, I hope you learned a little bit more about what frequency is. I hope it's a um, I hope I simplified it enough for people that are just going into engineering or are musicians and really were confused on what frequency was. And yeah, that's really all I have. So yeah, thanks for your time, and keep on learning.